Hi everyone, in this video we're going to be looking at how to solve volumes using cross sections specifically. And so what that means is we're going to be given a couple curves and we're going to be given what the cross section looks like. Now, before we go any further, I'm just going to give you a little pro tip as you're doing this in your notes here. It's a little bit hard for me using a tablet and not having the finest motor control with just like a pen and a stylus here. But just when you're sketching it out and trying to understand conceptually what things look like, instead of drawing your axes like perpendicular or parallel, I should say, to like the side of your book and the top of your page, you want to rotate it like 45 degrees so that when you go and sketch your curves, and then you go to draw your cross sections in the third dimension there, that you've got like a little bit of the third dimension to work with just for perspective's sake, so that you can kind of see, oh, that's not very good, so you can kind of see what's going on with your shape there. Because if you just use your regular like perpendicular axes like that, like it doesn't give you a lot of artistic room. But not to say that what I'm doing is exactly great here, but it just helps to see like what's happening. And so this is sort of like the spoiler. This is what we're talking about here. We're talking about drawing stuff and determining the volume of these kind of abstract shapes that if you were to slice them up, they all have the same cross section. So you can imagine like a loaf of bread. And when you cut through the loaf of bread, every single cross section is going to have the same shape. Now they're going to be of different sizes, but that same relationship is still going to hold true for that rectangular piece. And so when we're given two curves like this, the difference between the upper and the lower curve is going to give us what the width of our base is. And then you can imagine, so that red line I just drew, if I was to redraw it here in a traditional second or two-dimensional drawing, if I was talking about like a square cross section, well, then that red line, then the height of whatever that object is corresponds to the difference between f of x and g of x. So, I'll call this a. So if this is a right here, and we're talking about a square cross section, then this will also be a. Or if it's just a straight up f of x minus g of x, whatever the difference of those functions is, in the case of a square, can also be modeled or can be used to help define what the height is. Now, these are going to be the different cross sections that they'll give you. So clearly, if it's a square, just the straight up difference between f of x and g of x is going to give us what our height is. And so to calculate this is like a length times width calculation, or base times height, however you want to say it. If we're talking about rectangles, are going to give you some sort of relationship saying like that the height is twice the length of the base, or a quarter of the height, or a quarter of the height of the base, or a quarter of the magnitude of the base. They'll give you some sort of defined relationship. And again, that's the same calculation, so length times width. If they're giving you a triangle, so remember your core formula you're going to go back to is base times height divided by 2. You're always going to be able to figure out your base just by taking the difference in the functions. Now, depending on the type of triangle, you might have to do a little bit of math. I'll show you a shorthand for an equilateral triangle. A lot of times they'll just give you like a right triangle, which is nice and easy because then you just have to modify that length width and divide it by 2. And if we're dealing with a semicircle, then of course your core idea is pi r squared. The important thing to keep in mind, though, is when you take the difference and you're dealing with, now this is kind of hard for me to draw in that second, into that third dimension, I should say. So like if you've got a semicircle here, that difference gives you the diameter. So you're only going to want to use a half of that difference for your radius. And so that right there is pi r squared. And if they're actually giving circles, if that's what it is, then it's not really the base you're talking about. Then it's an actual like, should draw this with a dotted line. It's like this, it's a middle cut through is what this this difference represents, but I mean, it doesn't change anything. Oh, and if it's a semicircle, then of course you would take that area and divide it by 2 because you're only dealing with a semicircle. We'll get into some math here in a second. This is a little link here that you can click and interact with and play around with stuff. I'd encourage you to do it just to conceptualize what's going on. And these are just some pictures I grabbed from different GeoGebra just like little apps that other teachers and professors have made. So again, this is a better rendition of what's happening here, where you can see, okay, here's our square cross section. So this difference right here is the same as this this height right here. If this is in fact square, and again, if it's rectangle, you could have like just just a completely different shape altogether. But it's still going to be the same core idea of multiplying the height by the length, or height by the width of the base. If you've got equilateral triangles, This is just a handy little formula here to help. I'll just move this out of the way. So your area of each of your triangles is equal to root 3 over 4, and then the difference. So again, this is just our base rate here, squared. And this doesn't come out of anywhere. This is just like if feel free to skip through this, but this is just like derived from looking at the area of an equilateral triangle. So if I say this is x and x, and x over here, well, to figure out the area, I need the height. So then I'm going to use half of this x. So then I would go, so I would use my core idea of base height divided by 2, and then so 1/2 x. Sorry, I need the height, so I need to use Pythagorean theorem here. I'm gonna come over here. So height is equal to the square root of x squared minus 1/2 x, or height is equal to the square root of x squared minus, this should be all squared here, 1/4 x squared, or height is equal to the square root of x squared minus 0.25 x squared, so it just equals to 3 over 4 x squared, all square rooted. So if I square root this, then I'm going to get root 3 over 2x. And then if I go back to my original formula here, I'm going to have my base of x times my height of root 3 over 2x, all divided by 2. And so that's just going to end up giving me root 3 x squared, 2 divided by 2 will give me 4. And so that's where that's derived from. So it doesn't, it's not a magic formula. It's just generalization of an equilateral triangle's area. So let's just dive right in and do a few examples. So here we've got f of x and g of x, and we've got square cross sections. So how are we going to find the volume of this shape that's created here, this object that's created? Now, just to be clear, I know I mentioned, or I wrote in my formulas like f of x minus g of x. Just because I've defined f of x, this x squared is f of x, what's more important is for you to look at the upper and the lower curve. So it's always going to be upper minus lower. So in this case, my g of x is my upper curve. So you can imagine what's going on here is I've got, like if I look at each of these cross sections, I'm going to have g of x minus f of x. And then this is also the same as that. So when we're thinking about volume, what we're essentially doing is we're finding the area of each of these faces, and then we're imagining that, okay, they're going to have some width, but we want that width to tend towards 0. And as that tends towards 0, that right there is like our third centimeter or third meter, like however you think about it, because like if we just focus on area, then we only have a unit of centimeters or meters squared, but we want to get it to cubed if we're talking about volume. So this little thickness here is going to get us to that that cubic volume measurement, but it's getting smaller and smaller and smaller, so that we're looking at that as basically our d of x. And that's just a way to picture what's going on. So essentially what I'm doing is I'm going to integrate from 0 to 1. And I want to look and see like, okay, what's the area of my cross section? So it's just going to be g of x minus f of x all squared. And then I'm going to multiply, or you can think about it like multiplying by d of x, multiplying by that thickness there. But in reality, we're just talking about summing a bunch of different cross sections together and getting some number. So yeah, so I'm just going to plug this stuff in. So I'm going to have square root x minus x squared, all squared, integrating from 0 to 1 with respect to x. And I'm going to just expand that out. So this will give me x minus 2 root x squared plus x to the 4th power, all with respect to x. And then this middle stuff right here, I'm just going to do off to the side because that looks quite messy. So 2 root x squared is the same thing as 2x to the 1/2 x to the 4 over 2. And so that'll be 2x to the 5 over 2. So I'm going to rewrite that. I'm integrating from 0 to 1, x minus 2x to the 5 over 2 plus x fourth d of x. And now I can actually integrate. So this is going to be x squared over 2 minus 2 times 2x to the 7 over 2 all over 7 plus x to the 5th over 5 all on the endpoints from 0 to 1. And now what, this is multiplication here, by the way. Now what you would do is you would plug 1 in and plug 0 in and take the difference. When you plug 0 in, this all eliminates, so you just have to do it once. So the first time through, it'll be 1 over 2. I'll write it all in. 1 squared minus 4, 1 to the 7 over 2, all over 7. I know because it's 1 here, it's not going to change anything, but it's still good to just give you guys like the template there as to how we would fill it out. And then, of course, if this was any other number than 0, or if this was something other than a polynomial where it just all simply eliminated, I would have to plug in that 0 and like take the difference of whatever I get over here. But I don't have to do that here because I can see that 0, 0, and 0 is just going to evaluate to a 0. So this right here is the volume of that object there that's created by having square cross sections. I'm just going to leave it like that because I don't want to make this video a million years long just by doing some arithmetic. Feel free to simplify it on your end. So let's do another one. So here we've got two functions, f of x and g of x, and we've got rectangles that are twice the length of the base. Okay, so I've got a rectangle that look like this because they're like twice the length of the base. So my base is just created by taking the difference between the top and the bottom curve here, and this base is going to be 3 minus x, because that's my g of x again is going to be my upper curve, and then my width here, the height I should say, is 2 times that, so 2 times 3 minus x. So if I'm thinking about integrating, so it looks like it's going from 0 to 3, so 0 to 3. So if I'm, that's not a nice looking 3 there. So if I'm looking to figure out the volume of whatever that shape looks like, and I mean, if it's kind of like I'm not even sure what it would look like. So if it looks like that, let me just see if I can conceptualize this here. Ooh, this is not a good demonstration of my drawing abilities. Eek. So it looks something like this, I guess. Like a pyramid. I guess it's kind of pyramidal, like if you can kind of imagine what's going on there. But anyway, so from 0 to 3, so it's going to be 2 on to 3 minus x, 3 minus x, integrating with respect to x. I can take that 2 outside. And so it's going to be 2 from 0 to 3. I'm just going to do that math out. So 9 minus 6x plus x squared with respect to x. And then I'm going to actually integrate it. So 2, 9x minus 6x squared over 2 plus x cubed over 3 on the interval from 0 to 3. And again, once you get to here, you would take this 3 and you plug it into all your x's. Again, plugging 0 in is just going to evaluate to 0, so you don't have to spend time doing that step. Feel free to if you'd like to. And I'll just, again, I'm not going to spend time doing arithmetic in these videos. So if you have questions, by all means, shoot an email or message me on Teams. Let's do another one here. We've got rectangles that are like equal to the square of the base. So here we're just getting into more like, weirder and weirder relationships. So like if I'm drawing my rectangle here, so again, I've got the same function where the difference between these two gives me the base of my rectangle. And so that's going to be 3 minus x. And then the height is 3 minus x all squared. So this is an even more extreme version of what you saw in the previous video where it was just like a fixed 2-to-1 ratio. So again, this is going to look very similar where it's 0 to 3, and then it's going to be 3 minus x times this right here. I actually know what the square of that is right there, so I'll write it out. 9 minus 6x plus x squared, all with respect to x. And then, ultimately all I would do is multiply this in and then integrate and plug the 3 in. Once I've set this up, again, I don't want to waste time in these videos doing stuff that I'm hoping you guys are comfortable with. So if you have questions about this one, by all means, message me. But essentially, I would just multiply in and then plug the 3 in because I don't have to plug the 0 in once I've integrated, of course, because it just evaluates to 0. Let's see if we got something more interesting here. Oh, okay, semicircles. All right, something new. Okay, so here we've got, again, we're same idea where I'm going to always think about, okay, I've got the upper minus the lower, and then I've got these some shape here that's like a series of semicircles. So you can like kind of imagine what it would look. Again, yeah, it's hard to sketch in that. That's why we rotate our axes there. So if I could do this, I'll change colors here. Like this is something weird. So you got this difference here, and then semicircle, and this would be like this would be the bigger part. So you can kind of imagine like where's my other, let's do another semicircle, see if that helps me. I don't know what this would look like. It's kind of weird, like a weird loaf of bread, kind of with like a straight edge. But anyways, our core function for a semicircle is pi r squared divided by 2. So we're going to integrate from 0 to, it actually doesn't tell us here. I mean, I can get a good guess there just by looking at that. It's probably 1.5. I can prove it, of course. Clearly, it starts at 0. But to figure out where that intersection point is, you would set them equal to one another. And I can just tell through factoring that it's going to work. But here's, you would minus the 1.5x from both sides. And then you would factor out an x minus 1.5. And then you can see your two intersection points are 0 and 1.5. So that's where I'm going to integrate from 0 to 1.5. And I can just move the pi over 2 to the outside because those are constants. And my r in this case is going to be 1.5x minus x squared, all squared. And then you're integrating with respect to x. And so at this point, again, we're just like, once you set these questions up, they're just like, questions that we've been doing all along. So I'll expand that one out. So we'll get, what's that going to be? 2.25x minus 3x cubed, and then plus x to the 4th power, integrating with respect to x. And then again, I would integrate at this point. So I have pi over 2 as my constant to the outside, 2.25 x squared over 2 minus 3x to the 4th over 4 plus x to the 5th over 5. And it's on that interval 0 to 1.5. Again, when I plug 0 in, everything eliminates, so I don't need to worry about minusing the 0 part. I'm just going to take that 1.5 and plug it into all my x's, and that will give me my answer. As a little aside, when you're doing cross-sections with circles or semicircles, you're always going to end up with a pi left over. So your answers in textbooks and on worksheets and stuff, they'll always be expressed when it's giving an exact answer as something pi. Okay, and finally, let's do some equilateral triangles. And so remember, we've got that quick little, so the core triangle function is base height over 2. Specifically with equilateral triangles, you've got this quick little reference that you can always use, the root 3 over 4, and then the difference between your functions all squared. And so I'm going to definitely make use of that if I can save some time. And I also picked this one too because here we're starting at 1 as opposed to 0. So I just wanted to do an example where you've got to actually do the whole substitution of both in. So I'm going to have root 3 over 4 as my constant to the outside. I'm integrating from 1 to 2, and the difference between this should be an x right here. That's a typo. I can clearly see it's an x because it's like a slanted line there. And I made the question. So that 1.5x minus x is just 0.5. All right, here, let's use fractions here, my big boy. 1.5x all squared. Oh, hello. All squared. And you're integrating with respect to x. So I'm just going to come down here below this line. And so we've got root 3 over 4. And then when I expand that out, so let me just do this right here, 1 to 2. So that'll be 1 over 4 x squared dx. And again, you can bring that 1/4 out if you want to at this point as well. So it's going to be root 3 over 16. And then I'll integrate and I'll get root 3 over 3 and integrating from 1 to 2. So if I actually calculate this out here, so it'll be root 3, 16 times 3 is 48. And then I've got 2 squared minus root 3, 16, and then times 1/3. Correct? Oh, and this, yeah, look at this. I almost forgot to divide by 3 right there. Yeah, all right. And then whatever this evaluates to would be the area of that object with cross sections that are equilateral triangles. Anyway, so if you guys have questions, message me on Teams or shoot an email, and I'll see you in the next video.